Section 4.4.
Graphing sine and cosine functions without a calculator.
Exactly, because you don't need a calculator for this.
We don't need no stinking calculators.
Because we're going to teach you how to do it. We're going to teach you right now. So,
By hand.
Yeah, by hand. So whenever we have like sine of x here, there's something that happens every time that we graph sine of x. If all it is sine of x. And that is that, okay, it's in red. You can't tell that on your notes. There's not two colors on your notes, but you could color it now. Like you could go ahead and color this red one right here so that you can tell the difference.
Color it with a highlighter. Might
exactly,
be easier to see,
a highlighter or a different color pen.
Yeah, use a crayon or something.
Yeah, and so sine of x always starts here at 0, 0.
Right, every time?
Every single time. And then it always does one of these little curve things.
It's got like a hump,
by 2 pi.
A hump and a valley.
Yes, a hill and a valley by 2 pi. Okay, and we're going to talk about some of this here in a little bit, but that always happens. It starts at 0 and it goes up. It comes back down and the hill ends at pi. Then we've got our valley until we get to 2 pi. It goes up to 1 normally and it goes down to -1 normally. And it just keeps going back and forth between those.
Because it's periodic.
Yes, and that's what we mean by periodic is that these values like 0, 0, pi 0, 2 pi 0, those values keep happening over and over and over again that we get that 0. It's repeating itself.
So if you're just looking at the parent function of sine, this is the shape that you're going to have.
Right, and then everything else that we look at when we graph sine functions is some kind of a transformation.
Right, and it
just
follows.
Just like what we...
Yes.
Go for it.
You too.
Just like what we've talked about the entire year.
Vertical stretch, horizontal stretches, movement left and right, movement up and down, all those same exact rules apply.
In the exact same kind of way, just we start off with this as our parent function. So example 1, analyze the graph of sine x.
Let's do it.
Okay, so how about domain?
Domain is all real numbers because every value of x we can plug into that puppy.
Yeah, you can plug in anything for x and get some value for y. So all real numbers, which is negative infinity to positive infinity. How about the range?
The range would be, bye Gabe.
See ya, thank you.
The range would be from -1 to 1 because we don't have any y values outside of that particular
range of
range
values.
Of values.
Like we're never going to end up down here at -2.
Not with this base parent
ever,
function.
ever.
Right.
So that means that our range is from -1 to 1. Now, does that include -1?
It does, because if you were to take the sine of
something
of, let's go like 3 pi over 2 maybe.
Yep, sine of 3 pi over 2.
It's going to be -1.
It is.
It's not going to be close to -1. It is going to be -1.
Right. So it's kind of like with a parabola, how this would be kind of like a vertex of a parabola. It's similar to that. It actually really does touch -1, and it really does touch +1. Domain range. How about, is this a continuous function?
It is continuous. At no point in time will we ever pick up our pencil or pen, if you're one of those people, while we're drawing out the graph.
So we would say this is continuous.
Definitely continuous. No asymptotes here.
Okay, increasing, decreasing, or constant.
Oh my gosh.
This is the one that's a little unpleasant.
This is a little tough.
Because check it out. I would say that our graph increases from here until here.
Right.
And like this part of our graph, right here. And then it increases from here to here in the same sort of way, like our graph keeps repeating. But that's not the only place. Like, just in the part that we have drawn, we have 3 different places.
Right.
But
there's a pattern.
Okay, let's figure out that pattern then, right? So let's figure out what these points are, because we have 0, we got -pi, -2 pi. So in between here, in between -2 pi and -3 pi is -5/2 pi.
What if we did something a little closer to the origin? I think it might be easier.
Oh, okay, fine. So between 0 and -pi is -pi over 2.
Right.
Okay, and then between 0 and pi is +pi over 2. So we could say that it's increasing from -pi over 2 to pi over 2. And you can use brackets or parentheses on increasing in this case. Okay,
but not only that, it does it again a little bit further up the road.
Okay, so between pi and 2 pi is 1.5 pi, which is 3
pi over 2.
And then between 2 pi and 3 pi is 2.5 pi, which is 5 pi over 2.
Right. So then it increases from 3 pi over 2 to 5 pi over 2, but we don't have time to write down the infinite number of places that this graph increases.
No, we don't.
And Mrs. Stevenson and I, we like math a lot, but we don't want to write down all of the infinite number of times
we don't.
that
We
this
don't at all.
happens.
So what we would do for increasing is we would say, well, if you take negative pi over 2 and you add, how far apart is the starting values? Pi over 2 and 3 pi over 2.
Is that a pi? I believe that's a pi.
Those are pi apart because what we can do is we can subtract them. 3 pi over 2 minus a negative pi over 2. Oh wait, that's really like we're adding, ching ching, wall ball bing bang. So that's pi. They're pi apart. So what we can do is we can say, well, if I add pi to this, I get another interval. If I add pi again, that's another interval.
So it'd be like k pi, where
K
k
pi.
could be any integer.
Okay. And then the same thing with pi over 2, because pi over 2 and 5 pi over 2, those are also pi apart. So we can add k pi. And then we would at some point need to say like where k is
Any integer.
Any integer.
Any integer. Not a fraction, not a decimal, but an actual integer like
yeah
3
yeah
or negative
because we're
2.
saying if you wanted to find like 5 intervals where it's increasing, just start plugging in numbers for k like 1, 2, 3, 4, and you would get in those different intervals. Decreasing is going to work kind of the same way, right? Except that instead of the values we have, it's the other values. Like it's decreasing here from pi over 2 to 3 pi over 2.
Right.
So what we have to do in either case is we have to pick an interval to start off with. So on the first one we picked negative pi over 2 and positive pi over 2. Here I'm going to pick positive pi over 2 and positive 3 pi over 2. And then we add k pi
Right.
on both of them.
So there's your decreasing. Increasing and decreasing. And they should be on in-between intervals. Like they shouldn't match at all.
Yes. So that's increasing and decreasing. How about symmetry?
This guy actually has symmetry with, wouldn't we say the origin maybe? Odd? It's an odd function.
It's an odd function. It has symmetry about the origin because if we take this part right here, for example, from 0 to 2 pi, and we rotate it around, we get this right here.
Shut the front door. So you could graph this on your calculator. Turn your calculator upside down and be the exact same graph.
Right. Incidentally, I know we said we weren't using our calculator, but if you were to graph this on the calculator, what mode would you need to be in?
Well, you could graph it actually in radian or degree mode. However, the way that your calculator is defaulted when you graph it, you want to be in radian mode to get the true picture. If you just are in love with degrees and you want to graph it in degree mode, you have to change the window settings to go from 0 to 360.
Well, that sounds like a lot of work.
That's a few more button punches.
So what if we just always put it in
Just
radian
if you
mode?
leave it in radian mode, you'll be great. Now, if you're graphing on your calculator and you see a straight line and you're like, there should be some curves here, you're in the wrong mode. You need to go from degree to radian.
Yeah. How about extrema?
Oh boy, there's an extrema every pi units.
Every
Again.
pi units, because there's one right here. There's a max right here at
Pi over 2.
yeah, pi over 2 comma 1.
1, yeah.
And then there's another one here at 5 pi over 2 comma, oh, it's 1 again.
Hey, guess what? There's going to be another one 2 pi units later, because that's how long it takes to get back to positive 1.
Right. Every 2 pi, we've got a maximum, and then every 2 pi, we've got a minimum as well. These are 2 pi apart.
So here comes 2k pi.
Right. So pi over 2 plus 2k pi. But the 1 just stays like
it's always
every
1.
single time that was 1.
Never goes past 1.
Okay, where k is any integer. Our minimums then start like we can use this one, 3 pi over 2.
Yeah, 3 pi over 2. Yep.
And
Plus 2k pi.
yeah, I meant a plus, not a comma.
That's
there.
okay. Plus 2k pi. There you go. Good job. Good job.
And then it
Yep.
happens for our y value at
-1 every time. Period. End of story. Double stamp C's.
got it. What else do we need to do here?
No asymptotes.
No asymptotes.
There's
Now,
really no end behavior here because the end behavior doesn't necessarily approach anything in particular.
before we go there, there's no asymptotes, but this is bounded above and below.
It is bounded above and below.
And that's because we don't ever get to positive infinity or negative infinity for our y values.
Right.
So we could just say it's bounded, or we could say bounded above and below. Okay, back to what you were saying about end behavior.
The end behavior, if you'll notice on this, the sine function and the cosine function for that matter, because the cosine will be very similar to this, they bounce back and forth between 1 and -1. So if we were to look at the end behavior, we don't necessarily have specifically defined behavior as x goes to infinity.
Because it just keeps going back up and back down.
Yeah, the thing
it doesn't
never
ever
sits
start
still.
getting closer
Yeah.
and closer to some value. So would we say that this limit is undefined?
I would say that that's fair to say, or does not exist maybe. Hello, Mr. Allstat.
And same with the limit as x approaches
Positive infinity.
positive infinity of f of x.
The limit does not exist. I hear that's in a movie.
Mean Girls? Or some other movie.
I think Mean Girls, right?
Yeah, I don't know. I haven't watched it recently enough to know. So that's sine, and then here in a second we'll bust out cosine as well. But I think I'm gonna have to get rid of. I'm gonna need to get some room. I have to like clear this.
We'll make room. We'll do cosine.
Yeah.